right. So you already know who I am. I'm Lindsay Mico. I lead the data science program for Providence Healthcare. I really appreciate you guys coming here to see us. There's a lot of great content, but this is exciting work, and I'm excited to be able to share some of the work you've been doing around natural language processing, machine learning at scale. So, Providence. We are a not-for-profit healthcare company. Our mission is to serve all, especially the poor, the needy, and the vulnerable. We are a mission-driven organization. And as you can see from all these really big numbers on the slide, we are a big healthcare provider. We are in 7 states in the western US. And when you put all these numbers together, we have well over 20 million unique patients worth of data covering over a decade in our systems. So that's a lot of sensitive patient information. As good stewards of this patient data, we have spent the last couple of years meticulously, painstakingly building a hyper-secure cloud environment on top of Microsoft Azure. You can see a little lockbox there. We've spent a lot of time on security. It's first and foremost with everything that we do. And this is the big idea here. When you've been able to ingest the different data sources that you can see to the side of the screen, the electronic medical record, Epic, image data, genomics data, claims, transactional telemetry, when it can be ingested into a cloud environment and integrated, you can apply state-of-the-art machine learning and natural language processing at huge scale to surgically identify, obfuscate, and mask personally identifiable information within the medical record. This allows us to de-identify data in a way that's very different from traditional DID. The old-fashioned way is you ask one question, you define one cohort, you extract the specific elements that you're interested in into a static data set, you answer that question, and you move on. And that's fine, but it doesn't scale, and it leaves a lot, really the majority of the important medical information behind. You miss things. So we're doing it differently. Why does this matter? Well, first, there are times when data sharing can save lives. And we've been living through this COVID pandemic. Being able to share data from system to system lets us pool information and make better choices in the moment and help patients' health. De-identification can also help accelerate medical research. There's a lot, I'd say a majority of problems in medicine that are yet to be solved. And the ability to do advanced research on data at scale can really accelerate that. And the third is that when you can de-identify data using the approach that we're talking about today, where you retain the original structure of the medical record, you can do development, training, model testing, with a team of data scientists like my own inside our secure cloud, but against DID data. This adds another layer of security to our defense in depth approach. Over the past couple of years, leading this work, I've been privileged to work with a really great team of technologists, many of them from Tegria Services. My co-presenter, Nada, is one of them, and I'm going to pass the mic to her to introduce herself, Tegria, and tell you about the real work that we've been doing. Oops, there you go.
Great, thank you, Lindsay. Hi everyone, my name is Nada Tayeb. I'm a data scientist on the healthcare data science consulting team at Tegria. Tegria is the healthcare services and consulting company created by Providence to help organizations of all sizes optimize care, integrate technology, transform operations, and accelerate revenue. Bit of a mouthful. But for the past year, I've been working on de-identification of text data with Providence, with Lindsay and the team over at Providence. And so in my part of this presentation, I'm going to tell you how we're actually doing it. Okay, so let's dive into this. How to de-identify patient notes at massive scale. Well, first of all, let's talk on a practical level. What does it actually mean to de-identify a note? the typical patient note, and that's the note that, say, a doctor or nurse or somebody writes up about you in the electronic medical record. Well, the typical note is littered with identifiers, right? You have identifiers that are very, very sensitive, like your full name, your email address could be in there, a cell phone number, street address, you name it. Then there are slightly less sensitive identifiers, such as dates, for example, or your zip code or city, right? Less sensitive, but still an identifier. And then the names are actually something in between. So for example, a common name, if someone found that's not quite so sensitive. But a less common name could easily identify you. And names plus other identifiers could definitely help you figure out who exactly this patient note belongs to. So, what this example doesn't show you, I actually have to point out, is this example makes it look all sort of clean and tidy. In reality, a patient note is a hot mess. I mean, the dates are in an unbelievable number of formats. You can have names, first name, last name, spelling mistakes, phone numbers in all kinds of formats, weird punctuation that messes your model up, weird characters, and the notes can be very short, they can be very long. So they're super, super complex, okay? So with that, your very first step is to, one way or the other, you have to find a way to tag all these identifiers. So now you see in this example, you no longer know who that patient note belongs to, right? So you could say it's de-identified, except there's a problem. What if you miss an identifier? And the truth is that no set of rules, no model, and not even human annotators can be 100% accurate with something like patient notes due to the variety and complexity of this type of data. So the safer option is to do something called obfuscation. Obfuscation is where you replace all the real identifiers with dummy data, so it looks realistic, right? And if the model misses an identifier, now it's much harder for an attacker, who is someone deliberately trying to re-identify the note, to know that they found that that's real information, right? Whereas in that previous scenario, if you just stop at tagging, super easy, So okay, now we've de-identified one note. Well, what about 700 million? Okay, so how are we going to do that? And the answer is and can only be deep learning in the cloud. We are using, for our de-identification models, Spark NLP for healthcare, which is the licensed version of John Snow Labs. They're the ones that build Spark NLP. And we're using to do that tagging step, uses a type of model called named entity recognition. And that's where you have a deep learning model that's trained to find chunks of text and saying, hey, there's a date, there's a name, there's an ID number, and so on. And so essentially, the model takes in the text, converts the text into tokens, which are basically words, converts those words into vector representations, and then takes those vector representations and other character level features about each of the words, plus some other things, puts them all together and trains this very complex deep learning model, right? And the models are also pre-trained. So we're taking advantage of transfer learning, but the models can also be fine-tuned to your own data using the model training extension functionality. I should also point out the models are state-of-the-art, meaning that they are the best available on the market. Okay, so looks pretty complicated. Probably take a while to build this deep learning architecture over here. Well, I'll tell you the beauty of using Spark NLP, really for anyone that's used it, is that you don't have to know any of that stuff. You don't have to do any of that stuff, right? It's all bundled together for you in this simple, scalable, easy-to-use code. And I've put the code up here, not for you to read through the code, but just to give you a sense of how modular it is and how elegant it is and what it looks like. And of course, you're welcome. You can take a screenshot. You can copy this. It's also available on the John Snow Labs, their GitHub repo. This is basically what my code looks like, right? I mean, 68 lines of code to de-identify a patient note. Okay, so this is a geek out moment for the data scientists in the room. The data comes in. It goes through some pre-processing, tokenization, embeddings. I'm running to get my tags 2 different NER models plus some custom regex, merging the tags together. Okay, got my tags. I can also run obfuscation in the same pipeline. I don't have to do it in a different step, which is pretty cool. And I press play, out pops my de-identified patient node. Okay. So, thanks. Well, I don't think you have to applaud me. I really would have to give the credit to John Snow Labs, to be honest, on making that so simple. But let me tell you, it does take some experimentation to get the right setup, combination of models, extra regex to get it to work on your data. And but once you do get the hang of it, then you can get things rolling. Okay, but now what about, again, the 700 million issue? Well, the beauty of Spark NLP is that it's built natively in Spark. I mean, it's in the name, right? Spark NLP. Okay, so you take that code, you don't have to do anything. You can just scale it up in a Databricks cluster. Now, we work very closely with our technology partners at Databricks, and with their help, plus with some help from John Snow Labs as well, we were able to get a cluster to run 100,000 notes with 40 million tokens in 26.5 minutes. So not bad. Certainly pretty good for, say, a daily run of patient notes, but to do the full historical run, obviously, would take a few months. But you can see that this is just, we want to put some data out there for benchmarking if you're trying to do this yourself. And this will improve, as we're still working on improving this number. But OK. So I think the bottom line from this first half of my part of the talk is to say that amazingly, running these incredibly complex deep learning architectures at massive scale is, I mean, once you learn how to use the technology, okay, which takes a bit of doing, but once you get the hang of it, is the relatively easy part. Okay, so what's the hard part? What made this really, really, gave my brain a workout, all of our brains a workout, is this part, okay? So you think you've de-identified the patient note, but are you meeting HIPAA, right? So the hard part is meeting HIPAA. HIPAA gives you, in the US, for those of you that don't know, is the privacy rules that we have to abide by to protect patient data. So HIPAA gives you 2 routes for de-identification. The first route is something called safe harbor, where you have to remove 18 different types of identifiers, like names, dates, addresses, and so on. This only works for structured data. To do any kind of unstructured data, you have to go the expert determination route. Expert determination means that you apply statistical or scientific principles to determine that, based on whatever you're doing, that there is a very small risk that the anticipated recipient could identify the individual, okay? And by the way, safe harbor doesn't mean that there's no risk. It does mean that the risk is very low, but no risk doesn't mean no risk, and likewise with expert determination, right? But here's the problem, once again, the law doesn't give you a cookbook. It does not tell you what very low risk means, doesn't give you a threshold, and it doesn't tell you how to do it. So you have to figure it out on your own based on your use case. Okay. So with that in mind, I'm now going to talk about sampling, annotation, and evaluation. And I'm not evaluating this model as I would your typical multi-class classification model, right? I'm thinking about how do I evaluate the model in terms of its ability to reduce the risk of re-identification to a patient. All right, so keep that in your head for a minute, and let's dive into this. Sampling. So we need to draw a sample of these notes. And the sample has to serve 2 purposes. One, to tell us how the model is doing overall. But also we want to know, is this model fair and equitable? So we used a power analysis to come up with a sample size. This is our first sample. We actually have additional samples that we have annotated since then, more than double this number, but this is a good start. They're stratified by gender, race, and location. Okay? So we've got that. And if you want more details on how we did it, happy to provide it for you afterwards. And now we get to what is far and away the most difficult, the most time-consuming, and the most painful part of this entire process. which is human annotation. There's no way around it. You can't get an AI to do it. You, and if you're going to be doing this yourself, and your colleagues will probably end up will be the ones doing this most likely. Annotation. So how it works is that you take your sample of notes, you run it through the model to get the model's tags, and then a human has to go through and correct any of the mistakes by the model. And then at the end of this process, you get a labeled data set, which you can use to evaluate the performance of the model. Now, I promised some lessons learned, and I have to tell you, big lesson learned is that, one, you need to have a team of people. Two, you should have at least one clinical person on that team. Number three, you can't wing this. You have to create an annotation guide. You have to have a process. You have to have a review process. And number four, the quality control on this, it really takes a bit of time to get to an accurate labeled data set. But it's critical, because otherwise, how else are you going to accurately evaluate your model? Okay. This is another little detail that I think is really important, which is what happens when the model tags an identifier, right, but gives it the wrong tag. In this case, the zip code was tagged as an ID number. Is that a false positive, or is that a false negative? Now, in a typical machine learning evaluation, you say, well, that's not the right tag, that's a false negative. But since what we really care about is tagging and removing identifiers, for our purposes, we're going to call this a match and say it's a false positive. If you're doing this project, then you have to decide based on your use case what you're doing, how you want to handle these situations. But I just wanted to call that out as a detail. Something I wish I had known before I started this. Okay, I'm almost at the fun part where I show you some of our results. But before I get to that, I really need to spend a minute here, because I want everyone to really clearly and visually understand what I'm talking about, okay? We are using really two different metrics to evaluate the performance of the model. So one is at an entity level, right? So at an entity level in this toy data set, I have 10 notes. The 10 notes have 25 identifiers. We'll call them PHI entities, okay? And the model found 23 of them. So 23 divided by 25 is 92%. You can say the model found 92% of all the identifiers in the data, which, by the way, is the same thing as recall, but trying to keep the jargon to a minimum. But that's not good enough, because let's say you have 10 identifiers, right? The model misses one of them, and that one of them is, for example, something very sensitive. Let's say it missed a street address. I mean, your model isn't 90% accurate. It failed completely for that note, and potentially is compromising the identity of that patient. Of course, remember, all the data, the identifiers are obfuscated, so it's hard to figure out what's real and not real, but that real information is still in there. So there is a stricter evaluation method you really need to use when you're thinking about risk of re-identification. And that's looking at things at a note level. It's something called the percent PHI prevalence. So in this example, out of the 10 notes, 8 of the notes have some kind of identifier. So you can see a PHI prevalence is at 80%. Post de-identification, 2 notes still have some real information left. So the PHI prevalence post de-identification is 20%. So you can see how that's a much stricter way of evaluating how the model is doing. Okay, are you guys ready to see the actual results that we got on our 683 notes? Well, here they are. Out of that note sample, we had about 4,500 identifiers in total. The model found 98% of those, so hey, that's pretty good. However, on the PHI prevalence metric, we went from 75% down to 13%. Now, the first pass of this, it's because it's an iterative process. I got it to 21%, and after some work, down to 13%. So that's quite an improvement. But still, that still feels like, there's still some work to do. And isn't it kind of weird that that 2% of identifiers that were missed are spread out across 13% of the nodes? It's kind of interesting, right? So let's dig a little bit deeper to see what's going on, because if we can understand, maybe there are more improvements that we can make to this. Okay, so here you can see the results by entity type. Out of those 4,500 entities, over 80% of those were dates. Oh no, I'm sorry, this slide got messed up when we sent it from Google. I'm sorry, but anyway, I guess I'll have to tell you, it's 83% dates, and that larger chunk is about 11% names, and about 4% or so were ID numbers, and 2% everything else. And post-de-identification, that blue on the big circle is names. You can see that about 2/3 post-de-identification, out of the 106 that were missed, about 2/3 are patient names. So really what's happening is that the model is struggling on patient names. So that's kind of interesting. That's interesting. And then now we're looking at results by PHI prevalence in the notes. And so the blue bar is pre-de-identification, and the green bars are post-de-identification, and thankfully this didn't get messed up too badly. And again, you can see that patient names are still struggling. But here's kind of an interesting finding, which is some of the most sensitive identifiers, like email, street address, phone number, the prevalence of those have come down to almost 0%. So that's very encouraging. And then for the names, we've been working on it since this analysis, and we found a fix to really improve on patient names, and we'll be excited to report on that once that analysis has complete. But that's really the process. That's really what it takes to build a de-identification pipeline that's really, really good. And this is by no means the final pass. So with that, I've shown you a little bit about how the model is working for the patient population as a whole. But we were also talking about equity and fairness. So how is the model working if we look at it by race and by sex? And also we did it by location, but I'm not bothering to show that because there really wasn't too much difference by location. But it did make sure that our sample was well spread out. So we have this effectiveness metric where we do PHI prevalence after DID divided by PHI prevalence, before DID, after DID divided by PHI prevalence before DID. And so a number closer to 0 is green smiley face. A number closer to 1 is the blue sad face, just to simplify things, right? So let's look at by race. Now, interestingly, by race, the model appears to be underperforming on Asians, and maybe particularly on Asian names. So, but the sample size is very low. It's just 42 records, and the reason that it's low is because the patient population at Providence is predominantly Caucasian, right? Similarly with women, the model seems to be underperforming a bit, but we really need a larger sample size and more analysis to see if that's actually significant, but it's interesting. But I will tell you one really interesting and surprising finding. Look where the model is not underperforming, on other minorities. And by the way, other minorities also includes Hispanic. So because we thought that would be a problem, but it wasn't. So that was quite interesting. This is just an example of the type of work that Providence is doing in fairness and equity and really trying to fight the introduction of unintentional bias into machine learning. And you can go more to, Lindsay will be on a panel tomorrow if you want to learn more about that on fairness and equity, so we'll plug for that. But I think the bottom line is that we're committed to continuing to iterate on this work and on this pipeline until we are confident that this model is fair and equitable. And so with that, I hope you've enjoyed learning a little bit about how we're actually doing this at Providence. And I really need to give a shout out to all of my colleagues at Providence that have worked on this. It's been a huge team effort, multi-year team effort. This is just one little piece of the giant puzzle of de-identifying all of Providence's patient data. Big shout out to my colleagues at Tegria that have helped with this, particularly the annotation team, and to our technology partners, Johnston Labs, Databricks, and Azure, because without the technology, we wouldn't be able to do this. So thank you, and pass the mic over to Lindsay.
Thank you. So hopefully this comes across, but this is work we're still continuing on. What we've showed today is what we talk about as the last mile. It's probably a pretty long mile, but I think we're getting really close to it. But there are other parts to DID, structured data, dates, small text. we've solved all those problems. We have production pipelines that can do this. So I think we're quite close to being in a space where we can, certainly for the EMR, de-identify all the data all the time. But I will really emphasize the point that you made, is that equity analysis, the careful consideration of patient risk, we won't stop until we're done, and we really feel really comfortable that we've met the law, but more than that, we've protected our patients' privacy. So with that, I have one key takeaway message for you guys who just take one thing from this. That's Providence Healthcare has a blueprint for what a secure cloud environment looks like. And we can help you adapt that. Integrity Services can help you adapt that. We want to share what we've learned. It's part of our vision of health for a better world. And with that, I guess we can open up for questions.
I forgot to move it over to.
Yes, there was one more slide.
Thank you for that presentation. That was great. I enjoyed that. Actually, two questions. Hopefully that's okay. Did you train your own embeddings, or did you use some kind of open source healthcare embedding, or did you use BERT? I don't know if you used some kind of other embedding structure.
The embeddings come as part of the John Snow toolbox. Okay. There is, as part of that kind of ecosystem of tools, you can tune them with your own data. That's in our roadmap. Yeah.
Awesome.
But yeah, I think it's always good to build on what others have done.
Yeah, absolutely. And the other question was around names. Have you used any kind of parts of speech tagging along with your named entity recognition to help kind of influence that at all? I don't know if parts of speech was part of your inputs.
That's all rolled into how the John Snow Labs pipeline works. It does part of speech tagging and includes that as a feature in the named entity recognition. At least that's my understanding, into those models.
Awesome.
And to your question, each John Snow Labs model is trained using a certain type of embedding model, so you have to pick the right embedding model to match the NER or whatever other type of model that you're using.
Nice.
We think, for what it's worth, that the name issue is has more to do with the weird structure of medical notes. It's not like normal language. It's I thought it was going to be odd names that we were missing, but I went in, it was Deborah, Richard. I have no idea why, but it's got to have something to do with the kind of the odd syntax and structure of medical notes.
The context.
Yeah, but I think we have. But like I said, I think we have a fix. I'm not going to share it till we prove it, but we think we have a fix for it.
Cool. Thank you.
Thanks a lot for the talk. Can you speak about how you go about replacing entities such that if I look at a node, it makes inherent sense, right? Because as a human, I can see that this address doesn't fit with this zip code, or this name doesn't fit with this email address, or the domain is not valid or something, right? Can you speak about that?
I mean, I don't know if I totally understand the question. If it's Lindsay Maiko and you swap in John Smith, right? It just looks like a name. Same if if it's 1000 Main Street and it's 2000 South Street.
Right. I mean, if I were to go about breaking this or trying to re-identify the records, one of the first steps for me would be to try to identify which ones are artificially put in.
Right.
Right. So, and to avoid this, you have to make the entities look like they belong there, right? They have to be legit.
So you have to put them. You have to put the right thing in the right place, and you have to have a good representative corpus of them. I think and that's sort of the punchline of the answer. That trivializes it's simple on the surface, but quite hard inside of it. I think one of the things that for names, for example, is we have people's names in a structured field in the electronic medical record. That provides a corpus that we can shuffle around, right? We can do that for other fields. The other piece I'll note is, as part of the legal side to this, is that the last step in it will be adversarial testing by a third-party firm, where we'll run all this stuff, we'll write our expert determination, we're yeah, we think this is awesome. And then we're going to give it to a third party and say, okay, try and break this, prove us wrong. And that's where I think we're really going to see how well this works. I'm enthused for that. I think it's going to actually be but this is my hunch, it's actually going to be very, very difficult to figure out what's real and what's not, that the actual ability to re-identify will be vanishingly low, especially when you're at like a large scale.
Yeah, thank you for providing some insight to the important work you shared here. So question is to other data types, where are you in your journey for, let's say, imaging data as well as genomic data? Thank you.
We haven't started on de-identification of that per se. There's like, Providence is always on a journey, like our journey to the cloud and cloud migration started with EMR. Then we went to streaming. And this year, just getting image data, getting genomics data integrated into our Azure environment is the focus. And then once it's there and it's integrated, then we can move on to the de-identification. I mean, like, they are uniquely challenging de-identification problems. I have ideas, but I think my answer might be a bit rambling and would certainly be too long for here. But yeah, maybe next year we'll be here talking about that.
Hi, my name's Christian. I've got a follow-up question to the previous one, maybe helps clarify. Mm-hmm. And by the way, I think it was a great presentation, and thank you for doing this really important work. So I think in the obfuscation element where you, I would assume that you learn the probability distribution of your different identifiers. So just to give you an example, if there's this pregnant lady and you're going to replace the name or the date of birth, it kind of have to make sense. And also it can't be John Smith who's pregnant, and it can't be a 95-year-old. So do you learn that probability distribution and then replace, or do you just like, is there some sense checking that whatever is the combined record does make sense?
Yeah, right now in the built-in feature within the pipeline, it doesn't have that. So really you have to do some of that manually. Like for example, running male versus female separately to make sure that there's a male name versus a female name. For example, in the case of gender. But in terms of, I mean, for name, I guess you think, there are older sounding names versus younger sounding names based on generation, but it really wouldn't do that. Although it would be very interesting if it did. Cool. But right now, no.
If I may, I've got one follow-up question. That's
yeah, I will say though, like just
we
have discussed that, and that's something that the perfect implementation of it is not done. But I get what you're talking about. It's sort of this like conditional probability matrix, right? It's like given all these other things, how likely is the other part of it? I'm not sure it's strictly going to be necessary. I think we want to see when we do this adversarial testing, can an actual person really figure this kind of stuff out? But it's absolutely the right way to do it. It's absolutely on our roadmap. Totally, yeah.
Hey, hi. My name is Sapna. So I missed the initial few minutes of the presentation, so I'm not sure if you covered this. So I wanted to know how this de-identification of patient notes is going to help your stakeholders or customers.
How does it what with the customers? I didn't catch the last part.
How is it going to help your stakeholders or customers, the model that you have built, the results that come out, right? So how is that going to help?
Well, I mean, like our customers are sort of internal to Providence, right? We serve Providence as a system. This started for me as a way to help researchers. And it's, just for the record, it was people doing research inside our secure cloud, but being able to provide a de-identified data set, and it was an extract at the time, allowed them to do work pre-IRB. And even just to get metrics that they could use to define an IRB proposal, and so it went well. It was good, and I know my colleagues that are. I work in the IT department, right? And so like the idea of having de-identified data for a dev environment, that's been a dream of ours for a really long time. It's a challenge in healthcare because it's not like an email server where you can synthesize a bunch of it easily. So I know my stakeholders are really excited for it.
Hi, my name is Deepthi. Over here towards the left.
So in the beginning, you mentioned about the data was very messy. There were incomplete sentences and the spellings and everything. So did you end up using like BERT or anything for sentence completion, which were like not properly sentenced, or like the data was not very clean? So how did you manage that part of?
Well, it's managed because it's actually really managed, I think, in the embeddings layer, because there are embeddings that are trained specifically for clinical data. So it's able to take this really messy, awful patient notes and transform the words into vector representations that can be effectively used in a named entity recognition model for de-identification. Oh, you don't do any cleaning of the data. You just get the data and you stick it in there. That's the beauty of it. Yeah.
So, thank you very much, guys. It was really, really great talk.
Thanks.
Thank you. Thank you.
Thanks. Really appreciate it.
Have any questions? You can ask them in the in the hall or here
aftermath,
or whatever.
yeah. Cool. Thanks. Good job.
Really, really good. Thank you very much.
Thank you.
I'm gonna grab my
Thank
water.
you.